In all of the first-order circuit analysis problems we've done, I've only solved for capacitor voltages and inductor currents. In this video, we'll see how to use those variables to find other parameters in the circuit. In all of our examples and discussions so far, we've only solved for either the voltage across a capacitor or the current through an inductor. The reason for this is that these values describe the energy stored in the circuit. A capacitor's voltage completely describes the energy stored in the capacitor, and an inductor's current defines the inductor's energy. An important property of dynamic systems is that if we know the energy stored in the system, we know everything about the system that we need to know. The stored energy is also essential for determining the initial conditions. We take advantage of the fact that inductor currents and capacitor voltages can't change instantly. None of the other parameters in the circuit are guaranteed to have this property. So if we want to find initial conditions on some other parameter, we need to find the initial capacitor voltage and inductor current anyway. All of this means that we can always write an equation describing the energy stored in the circuit and then use that equation to find out anything else about the circuit that we want to know. I'll illustrate how this is done with a couple of examples from previous videos. The goal here is to show how to use the capacitor voltages or inductor currents to determine other values in the circuit. My first example is this circuit. The switch moves from here to here at time t equals 0, and we want to find the voltage V4 across this 4 ohm resistor. This circuit is the same circuit as in a previous video. It's just that now we're looking for a resistor voltage rather than the capacitor voltage. For time greater than 0, the switch connects the capacitor to the 12-volt source, and this is the circuit we're dealing with. Even though I actually want the voltage V4, I'm going to solve for the capacitor voltage. The basic idea is similar to nodal and mesh analysis. In those analysis approaches, I could ignore what I actually wanted to know about the circuit when I define node voltages and mesh loops, since once I'd solved for those values, I could find anything else I wanted. In my previous video, I found that this was the capacitor voltage for time greater than 0. Now I'll use that information to determine the voltage V4. If I do KVL around this loop, I get 12 volts is equal to V4 plus V of t. So solving for V4, V4 of t is equal to 12 volts minus this expression V of t, negative 7 e to the minus t over 6 plus 9. Solving for this, V4 of t is equal to 12 minus 9, which is 3 volts, minus a minus 7, which is plus 7 e to the minus t over 6. And there's my 4 ohm resistor voltage difference. My second circuit is also from a previous video, except in this example, we want to find the voltage across this 6 ohm resistor rather than the current through the inductor. For time greater than 0, this is the circuit that we're dealing with. I'm going to use this inductor current to find the voltage V6. I've already found that the inductor current is this. If I do KVL around this loop, V6 in terms of the inductor current is this voltage, 2 di by dt, plus the voltage across the 12 ohm resistor, which is just 12 times I. I need the derivative of current with respect to time, so taking the derivative of this expression, di by dt, is equal to, I multiply by negative 9, so that becomes negative 9. Negative 0.75 is the same as negative 3 over 4, e to the minus 9t, and the derivative of 1 with respect to time is 0. Now if I plug this in here, V6 of t is equal to 2 times positive 27 over 4 e to the minus 9t plus 12 times I, which is just negative 3 over 4 e to the minus 9t plus 1. Simplifying, V6 of t is equal to 2 times 27 is 54, 12 times 3 is 36, 54 minus 36 is 18 over 4 e to the minus 9t plus 12 times 1 is just 12. And this is the voltage across this 6 ohm resistor as a function of time. Although we can determine any value in a circuit from the energy stored in its energy storage elements, it's also possible to solve directly for any parameter we want to find. The solution approach to do that is identical to the approach we use to find capacitor voltages and inductor currents. But solving directly for an arbitrary parameter can be more useful from a cross-checking standpoint than as a primary solution approach. I'll use the circuit of example 2 to describe the cross-checks I usually do to verify my results. Since this is a first-order linear circuit with a constant input, any parameter in the circuit, including V6 of t, will be described by the solution of a first-order differential equation along with the initial condition on the parameter of interest. The solution of the differential equation will be in its usual form, as shown here. So V6 of t is equal to V6 of 0 plus the initial condition minus V6 as time goes to infinity, the final value, times e to the minus t over tau plus the final value of V6 of t. Finding the initial conditions and the final values on V6 provides a method for double checking the result I got earlier from the inductor current. First, I'll find the parameters in this equation. Then I'll use those parameters to check my previous solution. I'm not going to double check the time constant. We've already found that this is 1/9 of a second, and we double checked that result when we originally found the inductor current. I'll use the initial and the final values of V6 to check the previous solution. To find the final value of V6, we use the property that inductors behave like short circuits as time goes to infinity if the forcing function is a constant. The appropriate circuit to analyze is this one. I can use a current divider to determine the current through the 6 ohm resistor and then multiply that by 6 ohms to get the voltage. If I do that, I find that V6 of infinity is equal to 12 volts. To determine the initial condition on V6, which is the resistor voltage at time t equals 0 plus, we still need to use the fact that inductors can't change their current instantly. This is the appropriate circuit. I already found that the inductor current at time t equals 0 plus is 1/4 of an amp. At time t equals 0 plus, the 3 amp source is connected to our circuit. If I do KCL here, that tells me the current through the 6 ohm resistor is 3 amps minus 1/4 of an amp. To get the voltage across the resistor, I multiply that by 6 ohms. This is 11 over 4 times 6, which gives us 66 over 4 volts. This is the original solution of V6 of t we obtained from the inductor current. If I evaluate this equation as time goes to infinity, this term goes to 0 and V6 of infinity is equal to 12 volts, which agrees with our previous result. At t equals 0 plus, e to the minus 9t becomes 1, and this term becomes 18 over 4 plus 12, which is 66 over 4 volts. Since the two approaches agree, we can be pretty confident that this solution is correct. So far, our dynamic systems have had only one energy storage element, so they were described by first-order differential equations. Next, I'll talk about second-order systems, which have 2 independent energy storage elements and are described by second-order differential equations.